Thank you for staying so long. And I'm going to be talking about how we are embedding V8, the JavaScript engine V8, in the NativeScript project. How's the mood there? It's pretty quiet. Come on. Cool. Thank you. Cool. So before we start, just to make sure that we're all on the same page, we'll explain a few basic terms. First, what is a JavaScript engine? So JavaScript Engine is a computer program that executes JS code. Thanks, Wikipedia. And also, most modern JavaScript engines utilize just-in-time compilation. And when I first read that a few years back, I was like, wait, you just say compilation? I thought that I was writing in a language that's kind of interpreted and not compiled, and I was reading through different blog posts, doing some research, trying to figure out what is going on. Is my whole life a lie? Was I writing? Yeah. So it turns out that, yeah, JavaScript is interpreted, but it's not just that. The first JavaScript engine that was created was just an interpreter. But it turns out that we started using JavaScript for a lot of more things that it was initially thought it's going to be used for. So there had to be some performance improvements to the way the JavaScript engine works. So this is what actually the modern JavaScript engines do. And the blog post that I got it from is the JavaScript Startup Performance by Adi Osmani. You can find the link later. But the blog post says that this is actually a simplification of what JavaScript engine does under the hood. And I was like, okay, cool. So why do we actually need that? And as I mentioned before, well, performance, that's it. So the first just-in-time compiler embedded in a JavaScript engine was TraceMonkey, which is actually part of the SpiderMonkey JavaScript engine, which is owned by Mozilla. And it was back in 2007 or something like that. A little bit after that, V8 was released, and that was the same time when Chrome was released. And this really boosted the performance of JavaScript in the browser and everywhere else. And that kind of explains how the whole JavaScript engine development happened. And why is it, I mean, we started from just some interpreters, and this is what we've got now. So if you want to read a proper explanation of what a JIT compiler is, I really recommend this blog post by Link Quark, who was here today just 2 hours before, and I'm really excited to be on the same stage. Anyway, and another great resource is the talk Life of a Script, which is really recent, and it's by Satya and Jakub from the V8 team, and they're explaining all the optimizations that the V8 engine does under the hood in order to make JavaScript faster. Let's move on. I already mentioned that I'm going to be talking about V8. It is a JavaScript engine. It is built at Google for Chrome, and it was open sourced in 2008. And here I have this really cool video that you can check out later. It's by Lars Beck, who was the first tech lead for the V8 project. And what he said in that video is that V8 is not just something that Chrome uses underneath. You can actually take V8 as a standalone project and embed it at a different place. And this kind of worked out well, because Node.js embedded V8, and this is how we got JavaScript on the server. And what we're trying to do in projects like NativeScript is actually bring JavaScript to the mobile world as well. So NativeScript. A few words about me. I'm a developer at Progress. I'm part of the NativeScript team, and recently I became a GD for Angular and web technologies. Another important thing about me is that I love Webpack. I do quite a lot of Webpack things in NativeScript. And this is, I'm sure this is a Webpack error, but as you can see, I'm smiling because you have to accept these things. You know. All right, back on NativeScript. I'm going to tell you a story, a really short story. And I know, I mean, it's kind of weird, but I kind of had a long flight, and then I actually wrote that story, and then I cut it like 80% of it because it got even more weird. So that's just an explanation why it's like that. Anyway, so we have the JavaScript world, and we have these great magical creatures living in the JavaScript world. Not really technologically advanced, but they know a lot of spells. And they're kind of like elves, but not like the Santa Claus elves kind of type, but more like the elves from Lord of the Rings, like magical, handsome, awesome creatures. And another thing about the elves is that they're pretty expansive as a nation or tribe. And they kind of expanded the browser world. But here's the subtle difference. We shouldn't mix the terms browser and JavaScript because they're not interchangeable. There are things in the browser which are not part of the JavaScript language, obviously. The most obvious difference is the DOM and HTML, of course. Did someone say CSS? We're going to come back to CSS later. Anyway. Another important world in our story is the Android world, and the Android world obviously is populated by robots, which have really great technological knowledge, and they have a lot of native resources. And native resource, what is it? So satellites, geolocation, Bluetooth, camera, augmented reality kit, machine learning kit, basically everything you have on your phone today. The Android people take it for granted, and they have access to it. So I'm doing a really bad metaphor. The Android world is your mobile phone. Anyway. So what is the deal? The folks from the JavaScript world, the elves, are pretty expansive, and they want to use the native resources from the Android world. But they're not great diplomats. I mean, it's probably the whole JavaScript thing. Anyway, there is not a really easy way to use native resources from the Android world from JavaScript. And this is a problem that we're trying to solve in NativeScript. And if I say we, it's kind of weird because, yeah, NativeScript has been part of my life for 3 years. And if I say we, I mean the NativeScript team. And I know this is the same slide, but I was too lazy to change it. OK, so shortly, NativeScript is a framework that allows you to build native mobile apps for Android and iOS with JavaScript, or something a bit more sophisticated like Vue or Angular. Really short overview of the architecture. Obviously, we have Android and iOS on the bottom. We have the NativeScript runtimes, which allow us to have access to the native resources from JavaScript. Then on top of that, we have a common layer, which unifies the Android and the iOS APIs. So for example, if you ever had to build a user interface on Android and user interface on iOS, you would have realized that they're quite different. So we provide a common layouting structure or system that allows you to write the same code, and it should kind of work the same way on both Android and iOS. On top of that, we have a really, really small layer for the application framework, which gives you data bindings and navigation. And we also support Angular and Vue. And the last important bit is that if there is some library out there in the Android world, you can just wrap that as a Node package, ship it to NPM, and anyone can NPM install your package and use it in your NativeScript app. But today, we're going to be focusing on the NativeScript runtimes and how we access the native resources. And more specifically, we're going to focus on the Android runtime because this is where we embed V8. For iOS, we actually embed another JavaScript engine. JavaScript core, which is used in Safari. So native API access. Important thing about the elves. They're not just like not advanced in technology, they also don't have great scientific knowledge, but that's fine. So even if they had access to the native resources, they wouldn't really know how to use them. So what they do in that case is that they send out some spies in the Android world, and these spies gather information about the native resources. So they go back to the JavaScript world with that information, and now the elves know how to use the native resources. But they have to get there. So we're still not quite there, but they know how to use the resources. How does that look like in a more boring way? So we have a native library, for example, Android SDK or some animation library in Android. We parse through the whole library to generate metadata. Basically, we get every package, every API that's available, and gather information how we can use it. So if there is some method, we should know how many arguments the method accepts, what are their types, what is the return type. So we gather all that information and package that inside the application itself in some binary format. And the application package itself is not very different from a regular Android application. So we have just the Android application. Inside it, we have the JavaScript code as some assets. And to execute the JavaScript code, we also have a library which contains the NativeScript runtime and V8, which is the engine that can execute JavaScript. We run the application, the library starts, we initialize V8, then we set up some callbacks that we're going to take a look at right the next slide. And then we launch the regular Android activity. And we have a normal Android app running. So callbacks, very important if you are ever going to embed V8, callbacks are everywhere. First, we have a field getter callback. So const object equals java-lang object is actually a valid JavaScript code in NativeScript. Java comes from something that we set on the V8 instance as a global object because it was inside the metadata. So we know that we can access the Java package or Java because it's available in the Android world. Java-lang is actually where the field getter callback is attached. So whenever someone calls Java-lang from the JavaScript world, we trigger that field getter callback, and the callback finds the metadata inside the Java-lang package and returns what is exactly there in that package, what we can use. And finally, Java-lang object just returns the object class from the Java-lang metadata, kind of. Constructor callback. Okay, whenever we try to create a new instance of something in the Android world, we trigger a constructor callback, which was placed there by the NativeScript runtime. So the constructor callback creates the object in the Android world, and it also creates a proxy object in the JavaScript world, and then returns the proxy object. The method callback. Okay, so what is special about the proxy JavaScript object? For example, if we have two methods in the Java object, we're going to have exactly the same methods in the JavaScript object. And in these methods, we attach a method callback. So whenever someone calls that method on the JavaScript object, it's going to trigger that callback, and the callback is actually going to call the original Java method. And after it's called, we're going to get some result, and we're going to pass it back. And this is more of an implementation detail, but we can't actually just pass back the return result to the JavaScript function, but we have to set the result as a return argument of that proxy function or method. Okay, so far we know that we have metadata, but it is exactly, it's actually not enough to have metadata in order to call stuff on the native Android world. So we're using something called JNI, or Java Native Interface. And because currently we started V8, this is one virtual machine. We also have the Dalvik virtual machine running on the Android device. JNI is the thing that passes all calls from the JavaScript virtual machine down to the Java virtual machine, and the same way back. This is the actual bridge, if you ever heard of a bridge inside of NativeScript. Okay, but there's a little complication here. What happens if the Java object, the Java method, returns a string? Well, the string is going to be of type Java lang string, which is definitely not the same as a JavaScript string, or a string object, or even a string primitive. They're just two different data formats. That's why we need some kind of marshalling service that can convert data from the Java world to the JavaScript world and vice versa. And maybe you would ask, if you think more about it, what about objects? I mean, wouldn't it be terribly slow if we start converting objects from the Java world back to JavaScript? Well, actually, this is why we create proxies. This and, of course, attaching method callbacks. So we use marshalling for primitives and arrays. And obviously, the marshalling service and JNI are C3PO in our already weird story, because C3PO is a protocol droid, so it translates messages back and forth. And yeah, really proud of that comparison. Cool. So let's see very quickly how that works. We're trying to instantiate a new native object. We call the constructor callback. This requests an instance of the class from the Android virtual machine. We get back the instance of the class. We create a JavaScript proxy object and return it back. Then we try to call some method. We call the method callback that was attached on the proxy object. Then through the method callback, we call the actual native method. We get back the result from the Java world and then convert it to a JavaScript data format and assign it to the variable. So far, so good. Okay, are you ready for, I have no idea how much time I have, but it's just getting interesting. Cool. Let's talk about multithreading in JavaScript. Weird. Cool. I will try to explain the term junk, or there are a lot of ways to call that behavior. But here's the thing. Most of the devices that we're using nowadays have to draw something 60 times per second on the screen. So this is what we call frame rate. The frame rate of a usual device nowadays is 60 frames per second. And that means that we basically have 16 milliseconds to draw a single frame on the device. And that means that whatever computations we're doing right now, we have to finish in 16 milliseconds and be ready to draw something on the screen. And of course, 16 milliseconds is the upper boundary, because there may be other computations happening, and this may be actually down to 10 milliseconds in the browser, which is not a lot of time. And what happens if we fail to meet that 10 milliseconds? Well, we drop a frame, or we skip a frame. And when we start skipping frames, weird things start to happen. And this is the term junk. Okay, I'm going to put that on a really slow motion so that we can see the actual animation. Cool. I'll remove the ad. Awesome. So here we have a really smooth animation running in 60 frames per second. Focus on the, I just realized this is a beard. I thought it's a scarf. Anyway. Yeah, so focus on the beard. 60 frames per second. Looks pretty cool. Here, it kind of skips a few frames, right? 15 frames per second. You can definitely see the difference between this animation and this animation. So this is called junk. And it's very obvious when you start scrolling and the list just stops or lags. Cool. Why is that important? Well, we run the JavaScript in NativeScript on a single thread. And that is obviously the user interface thread. So that might cause junk in some cases. It won't cause junk if you're using NativeScript the right way. No. If you're building user interface, you won't have any problem because NativeScript is using native components underneath. If you're building animations, that won't be a problem because underneath we're using native animations and so on and so on. But it will cause junk if you're executing CPU-intensive operations. For example, if you're trying to calculate Fibonacci numbers in a very unoptimized way, which is something we do in our everyday lives, perfect example. So this would cause junk because it will stress the main thread, and the main thread won't be able to put out frames in 60 frames per second. So how do we solve that problem in JavaScript? Well, the browser has web workers, and in NativeScript we call them worker threads, but basically they're just background threads or separate threads than the user interface thread in the JavaScript world. Okay, the deal with the worker threads is that you can create them, they can do some computations in the background, and then they can return some result. That's the whole thing. The downside in NativeScript is that you can't share JavaScript memory, you can actually share native objects, and also the communication is limited. So it's not a great idea to return really large objects, or recursive objects also can't be returned. Okay, some V8 time, the really interesting thing. What is an isolate in V8? Well, this is a running instance of the engine, and it's actually V8's way to allocate memory for some script that's running and isolate that memory so it can't be accessed from other processes. And also, you can have many isolates, and they can run in parallel. Another similar term, or related term, is a context. One isolate can have multiple contexts. The contexts can't run in parallel. So basically, when you're running a script in an isolate, you should explicitly specify the context. What is the context right now? So how do you think we implemented worker threads? With isolates or with contexts? Isolates. Contexts? We didn't implement them? Okay. Well, the answer is isolates. And everyone who raised their hand, who was no one, guessed right. Cool. So worker threads are isolates. Basically, you create a new instance of V8. You attach some callbacks so that the two isolates can communicate, and that's how you have worker threads. And the way they work in browsers is pretty similar. Okay, last thing. Snapshots. Let's talk about the time. And I don't mean that I'm running out of time, although that's true. But what takes time in mobile applications? And more specifically, what takes time on startup? Well, obviously on the mobile device, we don't have network requests. All the scripts that we're running when we're starting the applications are already on the device. But we have to get them from the file system. So that takes time if there are many files. Also, parsing and compiling JavaScript takes time because JavaScript engines. And how do we solve the problem? Yeah, actually, these two things can take quite a lot of time. And this is a screenshot from 2 years ago. And at the time, that was how much it took to start the NativeScript application in a very unoptimized way, of course. And 2 seconds just to load the JavaScript of the app. It's kind of weird. So how do we solve that problem? First, we can bundle our app. So we can use a tool like Webpack to get all of our millions of files in our application and output a few files, for example, 2. So that way, we won't be making millions of file requests on startup. We will be making just 2 file requests. And parse and compile, obviously, we can't skip that part. We just have to execute our JavaScript code somehow. But there's this trick, which is called custom startup snapshots, which is a really great feature provided by the V8 engine. And I'm not sure if it's the only one, but it's definitely not provided by JSC. That's why we have it only on Android. So the way it works is that you take a JavaScript file, you run it through some generation tool that outputs, that executes the code, and then you take basically a snapshot of the heap at the current time and output that in some binary file. And the binary file gets in your in your application package. And when you start the app, you load the snapshot binary. You set some parameters for the isolate, passing the snapshot binary. And then when you create the new isolate, you can basically instruct it to create the new context from the already loaded heap. So it doesn't have to load the JavaScript from the file system, compile it, parse it, whatever it does underneath. And it basically takes these 2 seconds to 0. And this is a little bit of code. And if you're interested, I'm not going to read it, obviously, because I don't have time. But you can find it in the slides later. I'm going to share them. And this is actually a C++ code. But the idea of that code here was that it's not that hard to get a grasp of how you can embed V8. It's pretty, actually, understandable API. OK, what are the limitations of the snapshots? Basically, we're executing the code at build time. So we don't have any access to the native Android or whatever APIs. Also, we don't have require. And I don't have time to explain that, but find me later. I can talk to you about require, where does it come from, and why it's not a JavaScript thingy, actually. Anyway, also third-party code can break the snapshots because we're not sure if the third-party code is not trying to access something which is not available at build time. So how can we solve that? First, we can wrap native API access. Here, obviously, we're trying to access new Android text format time. And if we execute that in a bare context without metadata, without JNI, we don't have Android. So this is going to throw an error. The way to fix that is just to wrap that in a getter function and get the time lazily inside the other function that does some complicated things. That's the whole deal. And if you're really lazy, I don't have time to explain that code, but you can create getters like that. I'm going to give you just a few seconds to wrap your hand around the first thing. It's a very interesting function. Yeah, I still don't get it. Anyway, so the idea is that you have to be lazy when trying to access native APIs. And just a really quick reference, The editor Atom is using snapshots to optimize their startup time as well. And they have a great blog post on how they used heap snapshots to do that. And garbage collection, and obviously if I start talking about garbage collection right now, we can just flow into the next day. And, yeah. If you're interested in how we are trying to synchronize to garbage collectors the V8 one and Davix one, you can check out this blog post. It's a very interesting problem. And that was it. Thank you.